Hello everyone, I'm Kushagra Gupta and today I'm going to talk about understanding limit superior and limit inferior. First, recall supremum and recall that if a set S which is a subset of R has a supremum M, then for all elements S of S, M is greater than or equal to S, and for epsilon greater than 0, there exists an element S such that S is greater than M minus epsilon. For infimum, this becomes I is less than equal to S and there exists an S belongs to S such that S is greater than S is less than I plus epsilon. Supremum and infimum can also be thought of as a tightest lid or a base, in a way that if M is the supremum, then it can be thought of as a lid which tries to contain the S which tries to contain the set S as tightly as possible. Therefore, if there is a lid M, then pushing the lid by an epsilon distance towards that set would mean that there will be an element S in our initial set S which would not be contained in that lid, such as if S is our set and this is our lid, then if we move the lid by an arbitrary distance epsilon greater than 0, then there would exist some element which would not lie in S, after moving that lid. Similarly, the infimum can be thought of as a base which would contain the set from above. That is, if we move the base by a distance epsilon upwards, then there would exist some element which would not lie in our new set. Now we move towards limit supremum and limit infimum. Limit supremum and limit infimum can be thought of by many ways, such as it can be thought of as the limit as n approaches infinity of this set. Now, as we see, as we increase n, this set reduces in size. That is, the number of elements of this set decreases. Similar for this set. We see that we are taking the supremum or the infimum over this set, which is the set of the elements of the sequence which have indices more than k, where k more than n, where k is the index which ranges from n to infinity. So, as we know that we are for lim sub we are taking the supremum over a set, and we are increasing the value of n, so the size of the set decreases. And if the size of the set decreases, then we can say that the supremum lowers in its value, because now we are taking the supremum over less number of elements. That's why we can also write lim sub as infimum of n over natural numbers supremum of a k such that k is greater than equal to n. So here we see that instead of taking the limit over n as n approaches infinity, we can write it as the infimum over the set of natural numbers. This is lim sub. So there is a one-to-one correspondence. For supremum, we have infimum over the natural numbers, and for supremum, we have the and for lim inf we have the supremum over natural numbers. The most important point here to note is that as n increases, the value of supremum in case of lim sub decreases because the size of the set decreases. That's why as n approaches infinity, this in turn becomes the supremum. This in turn becomes the infimum of all the supremums which we obtained over the natural numbers. Like if this is our set of supremums, as n approaches infinity, this set reduces in size, and we need to observe it until it attains a constant value, which the value such obtained is called as the lim sub. So in a similar manner that the analogy we defined for supremum, we also have the lid analogy for lim sub. So we know that we can define a lid AK which bounds the set from above, and it starts from kth position and goes to infinity. So we have our sequence. So we define AK as the lid which starts as the position k. So we know that as k increases, the lid either remains at the same height or it decreases. It decreases when we drop one or more elements. So essentially, the size of our set is getting shorter and shorter as we increase n, or in turn k. Similar to a lid analogy, we also have a base analogy where the base starts from kth position and it goes until infinity. So we know that as k increases, either the base increases in height or it remains at the same position. This happens because as we increase k, the number of elements decreases, so the height of the base increases or remains the same. Here example illustrating the same. Consider the sequence of the elements defined by minus 1 to power n 1 plus 3 by n as an. Now we need to compute limit supremum and limit infimum of this set or this sequence. One way to do is to calculate the supremums of all the elements, supremum of all the set which starts at the index n. We define this set as beta n. So we observe that beta n can be computed as for even values of n, we know that beta n is 1 plus 3 by n, and this is a decreasing sequence. So the supremum of ak where k is greater than equal to n is 1 plus 3 by n for even and 1 plus 3 by n minus 1 for odd n. Now once we obtain the set of beta n, we can compute the lim sup by calculating the infimum of the set of beta n over all natural numbers. So we can easily see that for even values of n, as n approaches infinity, 1 plus 3 by n approaches to 1. Similarly, for 1 plus 3 by n plus 1 for odd n, this approaches to 1. Therefore, either by calculating the set of beta n's for all n and then calculating its infimum, we observe that the lim sup is 1, or we can directly see from this graph that this starts from 2.5 and the lid gradually goes up to 1 where it attains a constant value and is the lim supremum. Similarly, for limit infimum, we can calculate the set of alpha n's, which is the infimum of ak where k is greater than equal to n, and we know that for odd values of n, since we are calculating the infimum, this is going to be a negative number. So this is 1, this is minus 1 plus 3 by n, and for even n, it is going to be minus 1 plus 3 by n plus 1. And so lim inf is computed by calculating the supremum over n of alpha n, which is minus 1, because as n tends to infinity, 1 upon n and 1 upon n plus 1 approaches to 0. I do have another example where we consider the sequence 0 1 0 1, and here beta n, which is the supremum of am where m is greater than equal to n, is 1, and similarly alpha n is 0. That's why lim inf, which is the infimum of beta n, which is the supremum of alpha n, is 0 because alpha n attains a constant value, and lim sup is the infimum of beta n and it is 1. Lim sup and lim inf are also defined over the partial order inclusion, and there it can be defined as here. This holds the value of supremum because in the partial order the union is sort of a greater than equal to process and the intersection is sort of a less than equal to process, and this holds the value of infimum. It is also the limit as n approaches infinity of union of ai for I greater than equal to n. This is the lim sub and lim inf for inclusion. There are some lemmas related to lim inf and lim sub, such as for a bounded sequence an, lim sub of an is greater than equal to lim inf of an. And for any two bounded sequences an and bn, if an and bn have the order as an less than equal to bn for all n belongs to natural numbers, then lim sub and lim inf over the sequences an and bn follow the same ordering. The last being the inequality between the lim sub of a set of two sequences an and bn, where the individual set of limits have their sum more than the limit of the supremum of the sum of the sequences. An easy way to see is that for the subsequences an plus bn is 0, while lim sub of both is 1 and lim inf of both is -1. Here I presented a short idea about limit infimum and limit supremum. There is also a lemma that if an is a bounded sequence, then there is a subsequence ank, and if there is a subsequence ank that converges to t, then t is the lim sub of an. This can be proved using the lemmas which we derived earlier. Thank you for bearing with me and being a part of my lecture. Thank you.